Okay, this tutorial is going to be a fairly brief one going over the components that you're going to find in the standard drivetrain on an FSAE vehicle. We're going to look at both a drive shaft mounted drivetrain as well as a chain drive afterwards, the key components into each system. Starting off, we're going to look at the drivetrain system, and this is more common to what you would find in a commercial vehicle or passenger vehicle as well, your standard minivan or sedan. You would just have a shaft linking your differential and motor together. This is the simplest connection, but also runs into some packaging constraints in our car, so it's not used quite as frequently as a chain drive will, but we'll get into that in a little bit. Starting off, we have our motor first. Now, because we are working with electric vehicles, our motors are fairly simple. They're generally just barrel-shaped blocks that get chucked in the middle of the car. Not a whole lot going in with them. It's just a voltage in, voltage out, and they get mounted up here. On these mounting plates, you'll notice these little discs in here are vibrational dampers, generally speaking just made out of a stiff rubber compound. The reason for including those where the motor mounts to is that the motor generates quite a lot of vibration, and there needs to be something to absorb that. If you just hard mount it onto the chassis, it would have a tendency to break off the brittle welds and cause a lot of vibration in the vehicle. So by attaching these vibrational dampers into here, you can help absorb some of that force and result in a smoother ride overall, and less loading on the weld points as well. The output shaft of the motor is on this end here. It's just a spinning shaft. It is bidirectional, as it is electric. It can go forwards or backwards, and runs into this coupling here, which is then coupled to the differential. In this configuration, what you're seeing is a solid coupling where this is just a flange that is then screwed down onto the keyed shaft here. There's a small keyway that this slides over top of in order to transmit torque between them. It's screwed down into place to held in there, and then bolted up to the likewise flange on the differential. A different configuration is you could have another vibrational damper in between these two shafts in order to help absorb some more vibration, and also help correct for misalignment. If this differential and motor are not completely centered, then you will have some misalignment issues, and you would want a little bit of leeway in your drive shaft in order to compensate for that and allow it to shift over a bit. But in this configuration, you're just seeing a solid mount. So this would then be the input into the drive shaft, or into the differential, sorry. So this is a rotating object. It is a flange that goes into this differential, and this differential that you're seeing here, this outer piece is just a housing. This is all a static component filled with oil inside of this, but we're generally referred to as a pumpkin colloquially in this area, filled with oil with some gears inside that mesh up together. The oil is just there to lubricate the gears properly, hence why it's all a sealed package, but all the moving components are going to be hidden and contained inside of this. So the input shaft will go through into a set of beveled gears, generally speaking, that allow the motion to transmit from rotational motion around one axis into rotational motion around two axes, going out into each of your CV axles here, which we'll get into in just another minute. You will notice there are a couple different types of differentials that you'll run into. The differential that we most commonly use is called a limited slip differential, meaning that the rotational speed of the output to each wheel can be slightly different. It is allowed to rotate independently of each other, but the differential provides some degree of locking force that helps keep these rotating at a similar speed in most conditions. An alternative to this is what's referred to as an open differential, meaning there's no locking force in between these rotational speeds, and they can rotate completely independently of each other. If you were to say lock up one of these entirely, then 100% of your power would be transmitted to the opposite end, so you could have one of these axles stationary and one spinning. That's not quite desirable for our vehicle though, because we want to keep a standard load on each one of the tires. So we use a limited slip, which helps transmit load between the two of them. And then finally there'd be a locked differential, which means that these two axles are locked together entirely and have to be rotated at the same speed. We don't tend to use that in a racing vehicle because as you're going around the corners, the wheels want to rotate at different speeds as they travel in a longer path or shorter path. Hence you want to have a little bit of slip in between the two of them, which is why the limited slip is the most common configuration. So through this differential, you get a large gear reduction in here as well. The motor itself is just a one-to-one output. There's no gears hooked up on this end. Inside the differential, the gear set we choose to match the gear reduction that we want for the motor. In this case, we're running a 4.3 gear reduction. But you could go lower, you could go higher, depending on the torque output of your motor and also the top speed that you want to be able to obtain. Because we're running electric, we only need to run a single speed. We have near 100% of our torque output from 0 RPM. Basically, from a complete standstill, we have all the power that we need. Hence, we don't need to have a transmission and multiple gears, such as an internal combustion engine would have. But also, we are limited in top speed based on the gearing that we choose. We can't amp that up at all with the transmission. We have to choose a gear that we know will get us to the top speed that we desire, while still providing the good acceleration characteristics. Alright, on to the next component. I guess if you look at the wings of the differential here, this will always mount in a different configuration depending on the differential you're buying. This one happens to mount on these wings to the outside here. There will be more rubber dampers inside that get clamped down onto to allow the differential to not quite shift around a little bit, but absorb a bit of the vibration and also allow for a tiny bit of misalignment. They are quite stiff though and don't move all that much. The next piece we'll go to here is the CV axle. There is a missing component here. There should be another flange coming out of this end that would look similar to the one you see on the input shaft of the differential. These here would be your output shafts, and there should be a similar flange that bolts into this CV joint. And it would just bolt in and allow it to rotate. What is important though is these joints themselves. One joint up here and one joint where the wheel is back here. This entire assembly from start to finish over here is called your CV axle. These are referred to as the CV joints, CV standing for constant velocity. What these joints allow for is a rotational motion, but also being able to pivot up, down, left, right. And so these joints allow for the wheel to move up and down by pivoting at either end. So the wheel can travel, the wheel can move forward and back slightly, but still transmit a rotational force from this end over to the wheel end. There are a couple different types of CV joints that can be used. Most commonly what we use is a tripod joint, and I'll show you a broken down one of those in a minute. But that is generally speaking just the lightest, simplest configuration you can add into an FSAE car. There are other options available that allow you to transmit higher torques, but at the cost of a larger package and more weight, hence they're avoided a little bit more. And then finally, through your rotational CV joint, you get your output at this end, which will mate into the wheel bearing, the wheel hub, which is then attached to your rim and allows the wheel to rotate. These joints are also plunging, meaning that they can move inwards and outwards to some degree, because as the wheel travels up and down through its path, through its swinging arc, it gets slightly closer to the differential and slightly further away depending on the swinging part it's at. Thus, you want your CV axle to be able to plunge in and out a little bit to correct for that change in length. It is a fairly small amount though, not super noticeable, but you do have to have it there to prevent binding. So next we're going to look at a different configuration, which is our chain drive configuration. This is a much more bare model so you can see the individual parts a little bit better. This is going to be a different motor here, still an electric motor, so still single gear, just with an output shaft on it, but this motor is much thinner but a little bit wider in diameter, so it mounts in a bit differently. This one is mounted transverse, meaning that the rotational axis goes horizontal to the car, whereas the other motor was longitudinal, meaning that the rotational axis goes lengthwise along the car. So here we'd have our output shaft on the motor, which is mated to a small gear, generally referred to as your pinion gear, and then we will run a chain from this gear up to our bigger gear on the differential. This would be referred to as your sprocket, or you can just call it your differential gear if you want to. Not an official term for it really. The reduction you're seeing here is a very small gear on the front, very large gear on the back to give you your desired gear reduction. And then on here, this gear is mated up to our differential. This is also a differential, although it looks quite different than the other one. The reason being that this does not include that big housing that goes around it, does not include those large mounting points, hence you're seeing a much smaller, more confined package. This will still have a limited slip pack inside of the gear that allows the output shafts to rotate at somewhat different speeds, but because we're not translating force from one axis to another, we don't have to have that same set of large bevel gears, hence this differential can be a whole lot smaller and it only has to include that limited slip component, not the gears, not the beveled gears that allow it to change direction. So you run a chain in between the two of them, into the differential spins. It allows the output shafts to go at slightly different speeds, although they are still forced together somewhat. And then the same idea here, where you have a CV axle running to your wheel, forces the wheel to spin around. The difference being here, we don't have the boots over top of it, so you can see the inside. This is what we would refer to as a tripod axle here, where you have 3 bearings on the inside running through this channel here. What this allows for is that the bearings can slide in and out of this channel lengthwise. They are forced to rotate as the channel rolls around, but they can also pivot up and down due to the nature of the bearing, allowing it to rotate a little bit inside of this specially machined channel. So that's the tripod housing. That's what we're using on either end of this CV axle here. The other components that you would notice here: large bearings to allow the differential to be carried and rotate around smoothly. The differential mounting plates, which are just there to carry the differential assembly itself and mount up to our chassis. The mounting points are not defined in this model right now, but we would see on either one of these holes, we can mate this up onto the chassis itself. And then out to the wheels. And that is a general rundown of the chain drive system. So now we've seen both the drive shaft version and the chain drive version. Either one of these is a viable choice, although we'll more frequently see the chain drive version in FSAE just because it is a much more compact system. You can see a drastic difference in between how large this longitudinal motor is, how big this differential carrier is, versus the chain drive, to a much more compact solution. The downside to the chain drive being that you have to deal with slack in the chain, whereas this is just a solid mount in between the output shaft and the input shaft here, and it's solidly mounted together. You're not going to deal with any slipping in that as long as you mate them and bolt them together properly. You're never going to run into issues with one of them being off. Whereas with the chain drive, the chain itself will stretch out over time due to the constant force being applied to it, and you will also have to deal with manufacturing tolerances on this, as the chain only comes in a limited number of links. You can only shorten or extend it 1 link at a time, which will be 10, 20, 30 millimeters at a time, and so you can't take up really small differences in the length of the chain itself. Hence, if you have any manufacturing issues where this gear and this gear are a few millimeters further or closer apart than you expected, you have to be able to take up that extra length in the chain somehow, generally speaking through some means of a tensioner. A tensioner example on this one: by having these rotating barrels here, we're allowed to pull the differential further or closer to the motor, and that allows us to take up that extra slack in the chain. You could also have a spring tensioner, which would push down on the chain with another rotating wheel and force it to follow a longer path essentially and take up a bit of that slack. There are a couple different solutions. Any of them are viable depending on how well you implement it, but they are always necessary in a chain drive. Otherwise, if you have slack in that chain, it will have a tendency to slap around a lot and damage other components, or fall off of the gear entirely, or just skip a tooth, which would be if you put too much force on it, it might skip over one tooth and not transmit that force properly. So plenty of issues that arise with using a chain drive, although it is light enough and a small enough package that it is still desirable for our vehicles. You just have to be conscious of the issues that you face and come up with solutions for them during the design process. And that generally goes over the designs of the drivetrain systems. And working, now that you've seen both the suspension overview and the drivetrain overview, these two systems have to work very closely in cohesion, especially at this wheel package where the CV axle and the wheel hub mates together. Consideration has to be taken into both systems when you're designing them, and so it is important to have a thorough understanding of the components that go into each system. So hopefully you've gained a fairly good understanding out of this, and you can take away some good knowledge of all the components involved in these systems.